Reaction mechanisms. So most chemical reactions occur in more than one step. It's not just a collision and bang, you're done. When we write a chemical equation describing a reaction, we usually just show what's known as the overall reaction. We look at the reactants that are present at the beginning and the products that are formed at the end. Any intermediate things are not shown because those don't hang around. So a reaction mechanism is going to show us a series of individual chemical steps by which that reaction occurs. And understanding exactly how the mechanism occurs can allow you to control that reaction. So it's a series of elementary or individual steps. Each elementary step represents the exact species that are colliding in that reaction. And finding out what the mechanism can be a pretty challenging task. So let's look at hydrogen and iodine monochloride reacting. So here we have hydrogen reacts with the iodine monochloride, and that forms hydrogen iodide and hydrogen chloride. Hydrogen iodide then reacts with another iodine monochloride and forms another hydrogen chloride and an iodine molecule. So the individual steps in that mechanism have to add up to the overall reaction. So let's look at what is the overall reaction here. So that's an intermediate. It's formed and it's used up. And so it doesn't show up in the overall reaction. We got H2 plus 2 iodine monochlorides, and that forms 2 hydrogen chlorides plus iodine. So that's the overall reaction. The hydrogen iodide here is a reaction intermediate. It's formed in one elementary step and it's consumed in another. So it's present as the reaction occurs, but when the reaction is all finished, it's not there anymore. So the reaction mechanism gives us the details of what's happening. What are the species that are actually colliding? When we look at this overall reaction, we might think that the hydrogen needs to collide with 2 of these at the same time to make the hydrogen chloride and the iodine. But that's not actually true. It collides with one of those, generating HI. The HI collides with another one and makes the HCl and the iodine. So, looking at chemical kinetics can help us to figure out what the actual mechanism of reaction is. All of this would be so much simpler if we could actually just zoom in and watch the molecules do what they're doing. That would be crazy cool. But we can't. So it's a little bit like a black box, where you put something in and something comes out and you have to figure out what's going on, what's happening inside the box. And that's what makes science challenging, and it's basically just a big puzzle, trying to figure out without actually being able to see what's in there, what's going on. So we measure the kinetics of the overall reaction, we can measure those, and then we'll work backwards to write a mechanism that's consistent with the observed kinetics. The elementary steps are characterized by the number of reactant particles that are involved in that step. And it's called the molecularity. How many molecules are involved? So you can have a unimolecular step where you have one molecule decomposing into 2 or more products. That's not reacting with anything else, it's just happening on its own. Or you can have a bimolecular step where you have two molecules or two atoms that are the same reacting to form products. You can also have a bimolecular step where you have two different atoms or molecules reacting. You can have termolecular steps, three particles colliding simultaneously, but those are very rare. And, if you think about two molecules colliding and they have to have the right orientation and enough activation energy, to have it work out, then the odds of a three-molecule step, you can just see that that's probably not going to be a good thing to happen. It's just unusual. So we learned that you cannot figure out what a rate law is by looking at the overall chemical reaction. But you can figure out what the rate law is looking at an elementary step, because the elementary step actually reflects the collisions, the reactions that are occurring. So if we have a unimolecular step, the molecularity is 1, and that's going to be first order. The molecularity is equal to the order. So then the rate for that step is equal to a constant times the concentration of that one substance. Here are the two different kinds of bimolecular, and those are going to be second order. So you have a constant times A squared, or a constant times the concentration of A times the concentration of B. In those rare three or termolecular steps, those would be third order. And so you could have three of the same, two of the same, and one different, or all three different. Those are the different possibilities. And we can just, by looking at the step, we can figure out what its rate law is. Can't do that for an overall reaction, though. So more than one step. Usually one of those is going to be a lot slower than the others, and that's called the rate determining step. So if you think of a freeway, right? So here's an illustration of there's 3 lanes of traffic, but there's part where they're doing construction and it goes down to 1 lane. This section of the freeway is going to limit how many cars can get through the freeway in a given amount of time, right? Because it doesn't matter how fast people are going over here or over there, they all have to go through this one slow place. And so that limits your speed. Okay? So the rate limiting step is the slow one that limits how fast the overall reaction can occur. Does that make sense? So here's this reaction again. NO2 and CO forming NO and CO2. So the experimentally determined rate law is this. The rate is equal to the rate constant times the concentration of NO2 squared. Yes?
What do you mean by the slow one? How do you know it's the slow one?
It's always the slow elementary step that's going to limit the rate. Because all the other steps happen fast, right? And it's that one slow one. So once you get past, like in this freeway analogy.
But how do you determine which one's the slow one?
Well, that's a good question. How do you determine which one's the slow one? That's where you're looking at the kinetics and finding out which slow step would make sense for the observed rate law. So here's the observed rate law for the overall reaction. Could that be a single-step reaction? If this was an elementary step, what would the mechanism, or what would the rate law be? If that was an elementary step, meaning that this has to collide with this, the rate will equal a constant times the concentration of each of them, right? But that's not the observed rate law. We observe that the rate is second order with respect to NO2 and 0 order with respect to carbon monoxide. The carbon monoxide concentration doesn't have any effect on it. The fact that these are different tells us that this must have more than one step. So here's a possible mechanism. NO2 plus NO2 making NO3 and NO. That being a slow step. And then the NO3 reacting with the CO to form NO2 and CO2, and that one being fast. So this one's slow. Once that happens, this one goes really fast. So we can write rate laws for each of these steps. They're both bimolecular, right? So they're both going to be second order. This one is going to equal a constant times the NO2 concentration squared, right? Because it's going to depend on the concentration of both of those. This one is going to depend on the concentration of each of these, and so that rate is going to equal a constant times the NO3 concentration and the CO concentration. You can only do this for elementary steps. When we did it up here, it didn't match up with reality. Does one of these match the experimentally determined rate law? Yeah, it does. This one being the slow one, which depends on the concentration of NO2 squared, that's the one that limits the rate. And so this one happens as fast as it can after that NO3 is generated. So it doesn't matter how much carbon monoxide you have. Whatever's there, it's just going to react fast. And so we can identify that this mechanism agrees with the rate law. This is a possible mechanism. Can we prove that it's right just looking at these things? No, we can't. Yeah?
So we're always looking at the reaction, not the product.
Yes, we're always going to look at the reactant here, because we're looking at a forward reaction, and so we will get into equilibria, where the rate of, or the concentration of the reactant is messing with things as well, but we're not going to really worry about that right now. So in that mechanism, that first step has a higher activation energy. And so it has a smaller rate. It's slower. Once you get over that hump, you're rolling down, and that gives you enough. I mean, you can think of this as like a roller coaster or something. They need to pull you up here. You need energy to get up to there. But once you get up there, you've got enough energy coming down that it'll carry you up and over that one, and it's all good, right? This activation energy is much smaller, and so it's going to be faster than this one, and this rate equation is going to determine the rate of the overall reaction. That slow step is predicting the same rate law as the experimental data gave us. And that's how we identify that that would be the slow step. So for a mechanism to be valid, the elementary steps have to add up to the overall reaction. And the rate law predicted by the mechanism has to agree with the experimentally observed rate law. We can't prove them correct. We can validate them, but we can't prove that it's correct. You can show that a given mechanism is incorrect. There may be more than one mechanism that will fulfill those conditions. And then to figure out which of the proposed mechanisms is correct, you'd have to do further experimentation. I think that's a good place to stop.